I welcome you all to the session of engine system and performance, and today we shall discuss about engine heat balance. But before we go to discuss about this important topic, let us first recapitulate again a few factors those affect the performance of CI engine. If you can recall, in our previous module wherein we have discussed about SI and CI engines performance, and in that module we have identified a few factors those affect the performance of SI engine, and today we shall see that many of these factors also affect the performance of CI engine in the same manner. And let us first identify what are those common factors, and then thereafter we will see two important factors, those are very important to be precise. These two factors should be considered by the designer when a designer is designing CI engine for the better performance of the engine as well as smooth operation. So, if we try to write a few common factors, those are even considered as these factors affect the performance of SI engine. Let us now write these common factors are speed, then air consumption, number 3 is compression ratio. So, these three factors, if you can recall, we have discussed in details rather, these three factors affect the performance of SI engine. Now, if we know, so these factors also affect the performance of CI engines, and we will see in which capacity these factors trigger engine performance. So, we know that if we increase the speed, certainly power output of the engine will increase, that we have discussed in the context of SI engine. Here also increasing the speed of CI engine will ensure higher power output. So, that means this factor is also very important to be considered for the design of CI engine. Then what about air consumption? We all have understood by this time that certainly if greater mass of air is consumed by the engine, certainly greater amount of fuel can be burned and engine efficiency will increase. But the question is, and this is true for both the SI and CI engines, but in the context of CI engine, proper use or utilization of air is very important, and designers should design in such a way that the consumed air or the amount of air which is drawn into the engine cylinder should be used by the engine, so as to effective it becomes effective for the operation of the engine. Essentially effective use of the consumed air should be ensured. Then last one is the compression ratio. So, we all have studied in our undergraduate IC engine course that higher the compression ratio, certainly the peak pressure or the pressure rise at the end of the compression stroke will be more. And as I discussed, and you also have studied in your IC engine course, that higher rise in pressure is accompanied with a rise in temperature as well, and that too when that high temperature either air or charge will be combusted upon supplying fuel or spraying fuel, temperature rise will be even more. So, compression ratio if it is high, the power output of the engine will be high, and if you can recall the thermal efficiency expressions of thermal efficiency for both SI and CI engines, you can recall that thermal efficiency is function of RP, that is compression ratio, sorry, RC. Now, so but the compression ratio cannot be increased beyond certain limit for the SI engine, because it will lead to another detrimental phenomenon, that is knock. But for the CI engine, though knock is not there, but constructional issues will be there, because engine will be bulky, because to withstand that high pressure cylinder walls should be thicker, and that too some constructional problem will be there. So, all these factors affect the performance of CI engine, and designer will select all these factors judicially for the better operation of engine as well as to have maximum performance. So, in addition to these three factors, let me write here two another important aspects, and those aspects are really important for the operation of CI engines. Let me write here. So, the first one is two important factors, those affect the performance of CI engines. Okay. So, number one is, if I write here, number one is, this is known as injection timing. Injection timing means, in particular for the CI engines, what is done, air is compressed during compression stroke, and towards the end of the compression stroke, fuel is sprayed into the combustion chamber or engine cylinder. So, the injection time over which fuel is sprayed into the cylinder is very important, essentially for the peak pressure to be developed, and also total power output certainly. So, this injection time essentially refers the time duration over which the amount of, or the required amount of fuel must be injected or sprayed into the engine cylinder. Now, this injection times has to be adjusted so that rise in peak pressure should not be compromised, and at times engine operations should not be jerky or rough. So, these two important points you should remember. So, if I write here, so here injection time has to be adjusted, or I should write should be adjusted such that engine produces maximum power. Injection time should be adjusted such that engine produces maximum power without causing or inviting problem associated with the rough operation. So, without causing rough engine operation and producing undesirable smoke in the exhaust. So, let me tell you once again, you all have studied that if we just write this development of peak pressure. So, you know that if it is, so this called valve timing diagram, probably you have studied in the in your undergraduate internal combustion engine course. So, in the valve timing diagram what is done, you know that if I write here, so this is again, say for example, this is TDC, this is BDC and this is again BDC. So, you know that as the piston is travelling from BDC toward TDC during compression stroke, then you know the sucked in volume of air or the consumed amount of air will be compressed, and towards the end of the compression stroke. So, essentially you know air pressure will increase, and towards the end of the compression stroke, rather before TDC, actually for the CI engines fuel injection is you know started, because you can recall that in a CI engine the combustion process is mimicked by a constant you know pressure heat addition, it is not a constant volume heat addition. So, in a constant pressure heat addition, it is assumed that first part of combustion, so basically fuel injection will start before piston reaches at TDC, and that it will continue when piston will again travel back from TDC towards BDC during power stroke. So, this is essentially the compression stroke if I write here. So, this is compression stroke and this is the power stroke or expansion stroke. Now, what will happen, you know that if so piston is travelling toward TDC, if we have the peak pressure, so here then engine will be having, so if it is a case that when piston is coming back from TDC towards BDC and by that time second phase of combustion will be completed. So, the piston is coming down from TDC to BDC and the rise in pressure because of this combustion will try to create some jerky motion of the piston, and that is shown by here. So, essentially you try to understand the fuel injection period or time of or injection time, that is time duration over which fuel should be injected, is very crucial for the you know smooth operation of CI engine as well as better performance. Why better performance? You know that if it is a case that substantial amount of combustion is taking place when piston is coming back or travelling back from TDC towards BDC, then you know instead of, because already piston has travelled back from TDC to BDC. So, the power that will be produced because of the combustion will not be utilized. So, hence we need to compromise with the efficiency or power output of the engine and the operation will be jerky. So, this point is very crucial that injection time should be adjusted, and typically 20 degree before TDC to 0 degree TDC. So, this is essentially the fuel injection duration what is typically followed for the design of CI engine. That means, fuel injection will start when piston is 20 degree before TDC and it will be completed at when piston is at TDC. So, this is very important. Now, if we go to the next point, you can understand from this I can write one point that pressure rise due to combustion has to negotiate with the expanding volume of the cylinder. So, the take home message from this particular discussion is the pressure rise due to combustion has to negotiate with the expanding volume of the cylinder. As the piston is travelling back from TDC to BDC, as if the piston cylinder volume is becoming more and more, so expanding. So, this is the take home message you should remember. Okay. The next point that I would like to discuss in this context is the port and valve timings, and that is point number 2. Okay. This is again important. Why this is important? So, we have studied that inlet valve is very important, that the closing and opening time of the inlet valve is crucial, so as to ensure that adequate amount of air or charge can be drawn into the cylinder. On the contrary, proper opening of the exhaust valve is again necessary, so as to allow or so as to expel the combustion gases from the cylinder into the ambience with very small pressure difference. That means, let me tell you one thing, if the exhaust valve is allowed to open even when piston has not reached the BDC, say if we go back to the previous slide, you can see that. So, this is the power stroke and piston, we are getting work output from the stroke only. Now, piston will reach at BDC, but before piston reaches at BDC, if we try to open the exhaust valve, then the pressure in the cylinder is relatively very high, and that pressure will allow exhaust gases to leave from the cylinder into the ambience. But if it is a case, then at the moment we try to open the exhaust valve, pressure inside the cylinder will fall, and instead of getting some work or output, the that work or the enthalpy or energy will be lost with the exhaust gases. So, proper opening and closing of both the inlet and exhaust valves are very important. Proper opening of both the inlet and exhaust valve is very important, essentially for the smooth operation of the CI engine. So, if I write here just one line, then it will be clear to you all that the timing of the valves, the timing of the valves, here timings refer to the opening and closing of the valves. Okay. So, I am writing opening and closing of the valves, right. Timings of the valves for both 4-stroke cycle SI and CI engines, are guided by the same logic. What is the logic? Logic is to induct greatest amount of air or largest amount of air if it is a CI engine, or greatest amount of charge for the SI engines, greatest amount of air or charge. So, this is logic number 1, and if we go to the next slide, we can write here logic 2 is to expel the combustion gases from the cylinder or combustion chamber to the to the ambience with the smallest possible pressure difference pressure difference, certainly you know that pressure difference is the driving force to have or to make any flow to occur, right. So, until and unless there is a pressure difference, no flow can take place. So, when combustion gases or exhaust gases are allowed to leave from the cylinder to the ambience, certainly there must be a pressure difference. So, if the pressure difference is really more, certainly the combustion gases can be readily moved or expelled from the engine cylinder, but as I have discussed few minutes back, if the pressure difference is more, because atmosphere the combustion gases are typically expelled to the ambience. So, that is atmospheric pressure. So, if the pressure difference is more, means the pressure inside the cylinder will be more. If we open the exhaust valve little before the piston reaches at BDC, then that higher pressure difference will allow quicker removal of exhaust gases, but we will not be able to utilize that pressure which will otherwise produce certain amount of work output. So, this is ensured that the exhaust valve design and the timing should be such that the combustion gases can be expelled from the cylinder to the ambience with the smallest pressure difference between cylinder and the atmosphere. So, this is the important point. Now, in this context, before I go to discuss about engine heat balance, let me tell you one thing that by this time, that in the context of both two stroke cycle CI and SI engines, typically one process is there that is known as scavenging. What is this process? So, incoming air, so ports are allowed to open, so that incoming air will automatically allow the exhaust gases to leave out from the engine cylinder. Rather, incoming air stream will, or if it is a CI engine, only air stream, if it is a SI engine, then it is air fuel mixture, that is charge. So, incoming stream of charge or air is allowed to expel the combustion gases from the cylinder. Now, when the combustion gases are leaving from the cylinder, if it is a SI engine, then certain amount of charge or fresh charge also will go away with the combustion gases. So, this is essentially a loss because that charge otherwise can be used to produce some energy. So, that part is very important. On the contrary, if it is a CI engine, it is not the charge, rather certain amount of fresh air will be leaving with the exhaust gases. So, if the amount of air is not adequate inside the cylinder, so the amount of fuel which will be supplied to the engine based on the design condition will not be able to burn properly. So, that smoke or some NOx emission will be there. So, and output will be compromised. So, these things are very important to be considered for the operation, rather for the design of both CI and SI engines. So, with this, now let us move to discuss about engine heat balance. So, if I go to the next slide, then let me write what is engine heat balance and why do we need to consider this aspect in the context of engine performance and operation. So, we all know that essentially we supply certain amount of energy in the form of fuel to the engine, and that energy is chemical energy that is stored in the fuel itself. Now, the fuel is burnt inside the engine cylinder in the presence of adequate oxygen, that is air, and then that chemical reaction or combustion reaction is exothermic. So, this reaction itself generates extensive amount of heat, and it is because of this combustion that pressure rises and also temperature rises because of this heat liberation or generation. So, what you can understand, the energy that is remaining stored within the fuel in the form of chemical energy, that energy will be converted into mechanical energy or in the form of heat, and that energy again will be converted to another form, that is the work. So, we are supplying energy to the engine in the form of chemical energy, that energy will be converted to another form of energy, that is heat, and eventually we will be getting some energy at the output shaft, and that is the work. So, heat would be converted to work. So, you have studied thermodynamics. Heat is regarded as the high grade energy, low grade energy, and work is regarded as the high grade energy. So, certainly it is not possible to have equivalent conversion of heat into work, because heat is low grade energy and work is high grade energy. So, you know that some energy will be lost. So, we are supplying certain amount of energy to the cylinder, then we are producing energy in different form, then some part of the energy being produced will be lost, and we will be getting some part of it at the shaft or output shaft. So, if we can really take an effort for the accounting of energy that is supplied to the engine plus the energy that will be lost plus the energy that is available at the shaft, and that accounting can be described using heat balance. So, if I write here engine heat balance, so engine heat balance, as I said you, it is nothing but the accounting of the energy right, that is supplied to the engine plus the energy or the plus the losses plus the energy that is available at the output shaft may be expressed by carrying out a heat balance. It is similar to the balance that is typically done by the people in a bank. That means the amount that is deposited, the amount that is withdrawn, and the balance amount. So, essentially as I said you, engine heat balance. So, heat is the energy we have studied in our basic thermodynamics course. Energy which is produced because of burning the fuel is heat, and energy which is available at the output shaft is the work. So, all these are energies. Now, as I said you, so energy fuel, inside the fuel chemical energy is stored. The fuel is burnt in the presence of oxygen, and then we get energy which is heat. Heat is generated because of the combustion. Now, so that is the energy available inside the engine cylinder. So, inside the cylinder. Now, from here we are getting work, that is also energy available at the shaft. So, energy is conserved. So, the amount of energy which is remaining stored in the fuel will be converted to another form of the energy, that is heat, and again certain amount of heat will be utilized to get work at this output shaft, while certain amount of energy will be lost, that we have studied, but the total energy will remain constant. So, that means the amount of energy that is supplied to the engine is not equal to the energy that is available at the shaft, and that is why we had to define efficiencies: overall efficiency of the engine, thermal efficiency of the engine, mechanical efficiency of the engine, volumetric efficiency of the engine. So, that means if we can take an effort for the accounting of the energy that is supplied to the engine plus the losses plus the energy which is available at the shaft. So, entire the process can be expressed by carrying out a heat balance, and that is the that is known as energy engine heat balance. So, I can understand I can tell you that the designer will design the engine so as to maximum energy can be obtained at the output shaft. Our objective is to supply certain amount of energy to get energy in the different form, rather in different form at the shaft. So, the designer of the engine should be very much careful so as to design each and every component, and having very good design, I should say, the output available at the shaft can be maximized. And if we need to know all these information, rather if the designer need to know exactly what would be the power output or output energy at the cost of the input energy, designer needs to know the locations or identify these places wherein certain amount of energy is utilized to overcome several auxiliary loads, certain amount of energy is lost through coolant, and certain amount of energy is utilized to overcome the frictional effect. So, let me tell you once again, in an engine output power is obtained or output energy is obtained at the cost of some input energy. Whenever a designer is trying to have or trying to design an engine, the designer must be careful in designing several components so as to ensure that the output energy can be maximized. If that is the case, then designer must know or must identify places or locations or sources where certain amount of energy will be lost or certain amount of energy will be used to overcome other parasitic loads. So, that the output power or output energy can be maximized at the cost of the input energy. So, if I write here one important point, that the heat balance is therefore a determination of the disposition of the energy which is provided to the engine in the form of fuel. That is the chemical energy, and this, so that this is essentially heat balance. And this particular analysis or accounting of all these energy budget rather helps, it helps to determine the areas which must be focused, for obtaining better performance. That means, we know the amount of energy which is supplied to the engine at the cost of that input energy. If we can identify the areas wherein certain portion of energy is used or utilized to overcome several parasitic loads, or certain amount of energy is lost through those areas, then it will help the designer to have more focus on those areas, so as to ensure that the performance of the engine can be maximized. That means, the output power or power available at this output shaft can be maximized. So, this is the heat balance. If we look at the typical heat balance of a SI engine, it looks like this. So, what we can see from this heat balance, as I told you, this is basically a typical heat balance. So, if I write, this is the typical heat balance or heat balance for a typical SI engine. What we can see from this diagram, that so percentage of the fuel energy, if we look at the y axis, you can see percentage of the fuel energy, that is 100%. So, energy cannot be created, cannot be destroyed. So, the energy that is available with the fuel, say for if it is 100%, out of this 100%, if we look at this diagram, we can see only roughly 40% is the indicated work, or certain amount of energy or heat is supplied to the coolant, certain amount of energy is carried away by the exhaust gases. That means, exhaust gases carry enthalpy. So, energy is getting lost. Certain amount of energy is transferred to the coolant. We all have studied that it is very irony is that we need to supply fuel to get some work output, knowing fully that we need to supply certain amount of energy to obtain certain amount of work. We are trying to take off or take away certain amount of energy from the engine itself by supplying coolant. That is where thermodynamics second law is very important. So, that means, any device cannot be operated with 100% efficiency. So, we know very well that we are going to supply certain amount of energy. Out of this 100% energy, you can see only 1/3 is the indicated work, that is work available inside the cylinder. Remaining 60% or even more than 60% of energy is used to overcome several parasitic loads, and almost out of the 60%, almost 30% is used, 30% is getting lost with the exhaust gases. So, if we look at this indicated work, that is only 1/3 of the total energy being supplied to the engine. This indicated work has again some components. If we look at the block diagram which is placed in the right panel of this diagram, we can see out of this total 1/3 of the total energy or total fuel energy is the indicated work, and out of this indicated work there are many components. The most important component is the brake work, and that is the work available at the shaft. Then we have pumping work. So, what is pumping work? This has two components. Engine or engines have one small pump, and that pump is used to supply water to the radiator or to supply water to the cooling water jacket, etc. Over and above that small pump, which is driven by taking certain amount of energy from the output energy, we all know that out of 4 different strokes, only one stroke is power stroke. So, remaining 3 strokes are ideal strokes. So, out of 4 different strokes, 1 stroke is power stroke and remaining 3 strokes are ideal strokes. And so, these 3 strokes, to execute these 3 strokes, we need to borrow energy from the output power. So, that is known as pumping. So, basically we need to pump the exhaust gases. So, exhaust gases should be expelled from the engine cylinder to the ambience through the exhaust valve, and that is the exhaust stroke. So, exhaust stroke pushes all the gases from the cylinder to leave from there to the atmosphere, and at the same time when piston is coming back from TDC to BDC during intake stroke, as if we are trying to pump certain amount of fresh air or charge into the engine cylinder. So, the energy needed to execute these 2 strokes are known as pumping energy. And then we have rubbing on frictional work, that means cylinder will move or reciprocate between these 2 locations continuously. So, the 2 mechanical components, when they are in contact each other, we really cannot ignore or we really cannot make the frictional losses to be 0. Certainly efforts have been taken to minimize the frictional losses, but still the rubbing effect of frictional loss will be there. This is the rubbing or frictional effect, and also there is one small component that is known as accessory work, or this amount of energy is needed to run several auxiliary systems for the parasitic loads. Say for example, in a passenger vehicle, if we have any air conditioning unit, to run this air conditioning unit we need some amount of energy, and that energy is borrowed from the output work. Similarly, for the passenger vehicle, during daytime there is no need of having any lighting system or requirement of light, but we may require to turn on the light, and the energy that will be used to turn on light will come again from the output energy. So, all these are parasitic loads, and these parasitic loads consume a small fraction of the indicated work, and all these components are given. So, that means we can understand the designer needs to know exactly the areas wherein certain amount of energy will be lost or will be used, and that information will help the designer to have more focus on those areas, to improvise those areas so as to maximize the brake work, and it will essentially improve or maximize the engine performance. So, if I write a few lines in this context, that the qualitatively energy balance can be better understood from this diagram. So, if we look at this diagram, we can have some information qualitatively about this energy or energy balance. So, qualitatively energy balance can be better understood from this diagram, but if we need to quantify, then let us write exactly what portion of output work is needed to overcome the or to run this pumping for the pumping work, what portion of the output work is needed to overcome the frictional losses, what portion of the output work is required to run the parasitic systems. So, if we go for quantification, let me write a few lines. So, if I write here examination of the quantitative aspects So, if we go to the previous line, so this is, and if we come here, examination of the quantitative aspects of the typical energy balance diagram as shown in the previous slide. So, this is very important. As I said you, having a look at this diagram, we can estimate qualitatively what portion of work is available at the shaft, what portion of input energy, then out of this, or what portion of the input energy is available inside the engine cylinder, then what portion of this work produced or energy produced inside the cylinder is available at the shaft, and then out of this output work or output energy, what portion of that output energy is needed to overcome the frictional losses to run the parasitic system and for the pumping work. So, this is qualitative, but here we are trying to write some quantitative aspect. So, let me write here. First is approximately one third of the fuel energy is lost as exhaust enthalpy. So, we have already seen from this map that exhaust enthalpy, that is exhaust gases carries certain amount of enthalpy, and that is one third of the total input energy. It's very, the substantial part is getting lost. Then number 2 is another one third is lost as heat rejected to coolant. So, we need to supply coolant through cooling water jacket essentially to save engine cylinder and other material from their mechanical failure, and the amount of heat that is rejected to coolant is almost one third of the total input energy. So, again it is substantial. Then frictional losses are generally manifested as additional heat transferred as heat transfer to coolant or oil. Then the most importantly, the brake power, brake work is nearly 40%, lower than the indicated work. The indicated work. So, let me tell you one thing, if we go to the previous slide, what we can see, if we look at this diagram, we can see out of this total 100% that is energy which is supplied to the engine in the form of fuel, one third is getting lost through the exhaust, by the exhaust gases, because exhaust gases carry enthalpy. One third of that energy that is heat which is lost, or that means certain amount of heat is transferred to the coolant. So, again this is loss energy, and remaining 1/3 is the indicated work. Out of this indicated work, the break work is even 40% lower than the indicated work. So, whatever amount of work that is produced, or whatever amount of power that is produced inside the cylinder, 40% lesser of that work is available at the shaft, that is break work. So, that 40% less which is not available at the shaft work is utilized to overcome all these accessory or parasitic loads, pumping work, that is to execute 3 other ideal strokes, and also to overcome the frictional losses. So, this is one thing, and just if we go to the next slide, last point I will write that pumping losses comprise approximately 5% of the total fuel energy. Right, and as I said you that only 40% brake power is nearly 40% less than the indicated work. So, this 40% lower, I mean this 40% work which is not available at the shaft is used to overcome, right. So, brake work is 40% less than the indicated work, and this 40% includes pumping losses, frictional losses, and parasitic loads. Okay. So, this is the quantitative estimate of the typical heat balance that we had discussed today. So, if we summarize our today's discussion, then it can be said that we had started our discussion on identifying factors those affect CI engine performance, and to this end we have again recapitulated all those factors, all the factors those affect both CI and SI engines. Then we have identified 2 important factors those exclusively affect the CI engine performance. Thereafter we had discussed about engine heat balance, why do we need to have this heat balance, and what is heat balance in the context of engine operation, and then we have discussed about a typical heat balance for the SI engine, and thereafter we had seen from the heat balance itself it is possible to have qualitative estimate of several areas wherein energy is lost, and then we have quantitative aspects of that particular heat balance diagram, and we had seen exactly out of the energy or total energy which is supplied to the engine in the form of fuel, how much energy is available at this shaft as useful work. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.